In geotechnical engineering, failure is rarely sudden. When a landslide occurs, we often hear one phrase: "It happened without warning." But the truth is, ground failure is not an event. It is a process. A slow, invisible process that develops beneath our feet, long before cracks appear on the surface. In Malaysia, incidents in places like Genting Highlands and Cameron Highlands are often perceived as abrupt failures. However, geotechnical data tells a different story. Ground movement begins months, sometimes years earlier, through creep deformation, stress redistribution, and changes in pore water pressure. The real question is not whether the ground was moving, but why we failed to detect it sooner. The most dangerous phase of slope failure is the one we cannot see. Early-stage instability occurs through millimetre-scale movements, progressive shear strain, and subtle fluctuations in pore water pressure. By the time surface cracks are visible, the failure mechanism is already well developed and the window for low-cost intervention is closing. Today, technology allows us to observe ground behavior across multiple scales. This new toolkit is built on three complementary perspectives. Satellites provide the macro view, drones offer high-resolution local insight, and in-situ sensors deliver continuous ground truth data. Together, they transform how we understand slope stability. Interferometric synthetic aperture radar, or InSAR, measures ground movement from space with millimeter-level precision. By comparing radar images over time, InSAR reveals deformation patterns that are impossible to detect through visual inspection. In Malaysia, this technology is particularly effective for monitoring cut slopes, highways, and areas influenced by intense rainfall and development. While satellites identify regional hotspots, drones allow engineers to zoom in. UAVs provide high-resolution three-dimensional models, enabling precise measurement of cracks, scarps, and deformation geometry. When deployed strategically, drones bridge the gap between regional monitoring and site-specific investigation. Satellites and drones observe from above, but sensors listen from within the ground. In-situ instruments such as tilt sensors and soil moisture probes provide continuous, real-time data. These sensors detect subtle changes in inclination and moisture conditions that often precede failure events. These technologies are not exclusive. Their true strength lies in integration. Satellites scan wide regions, drones investigate priority sites, and sensors monitor the most critical locations continuously. InSAR does not replace site investigation, it tells us where to focus our resources most effectively. Today's challenge is no longer data availability. We now collect massive datasets from satellites, drones, sensors, and weather systems. The real challenge lies in integration, transforming isolated data streams into meaningful, predictive insight. This is where artificial intelligence becomes essential. Machine learning algorithms can integrate diverse datasets and identify complex, nonlinear patterns that precede slope failure. By combining ground movement, rainfall, soil moisture, and terrain data, AI transforms monitoring into prediction. The vision is a unified platform that converts raw data into actionable intelligence. Such a system enables dynamic risk mapping, automated early warnings, and data-driven maintenance planning. This marks a fundamental shift from reactive response to proactive hazard management. The predictive workflow begins with regional scanning, followed by focused investigation, continuous monitoring, and automated prediction. Each stage builds upon the previous one, creating a closed-loop system for managing geotechnical risk. To realize this vision, several priorities must be addressed. These include algorithm development, standardized workflows, platform integration, sensor advancement, and the incorporation of nature-based solutions. Together, these efforts shape the future of predictive geotechnics. The ground beneath our feet is never truly static. For the first time, we now have the tools to see it move. By shifting from reaction to prediction, we can reduce risk, protect infrastructure, and build a safer, more resilient future.